Our job is to prove these trig identities. So you guys would have done some proving maybe a little bit in geometry. Okay, not sure how much you actually did or what you remember of it, but the idea of a proof, because that's essentially what we're doing today, is we're doing a proof, is to prove that one thing equals another thing. Okay, so if you look at example 1, okay, now example 1, this is technically, it says prove the algebraic identity, so you don't have to think trig for a moment. Okay, this is, we have this, essentially this equation, and our job is to prove that all this mess on the left, okay, because that's what it is, right? It's a big mess on the left. Our job is to prove that it equals 2. So our job is to work with simplifying that left side to show that it equals 2. We're not going to touch the right side of the equation. When you're doing a proof, you always have one side of the equation you're not going to touch. And so as we work with this, our job when we get down to the end is that this equals 2. Now, we're starting with the left. So let me write it in up here. X squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1. So all we're working with is the left there. And our job in the end is to show that it equals 2. To manipulate it, rearrange it, do whatever we can with it to show that it equals 2. Thoughts on what we can do with these two fractions here? Okay, and there's a couple of different ways we could go with this depending on what you see. That's a lot of what it comes down to. What thoughts do we have, Ross? Okay, so one option, we see two fractions being subtracted, is to get a common denominator. And we can go that way, although I'll be honest, it's not the easier way. Okay, I'm not against it. It's just not the easier way in that particular situation. And I get it, and it's a good idea in that, when we see fractions, what do we often try and do? Put them together, yes? I get it. Do a little inspection of those numerators. Yes, they're the same. That's not what I'm looking at. What else do you notice about those numerators? Besides the fact they're the same.
You could factor those into like x minus 1, x plus 1.
Okay, x squared minus 1, does that factor? And if you'll go with me, you'll see why I would prefer that we factor it as opposed to getting a common denominator. It'll make life easier. Okay, so x squared minus 1, this is what I call the difference of squares. X squared breaks into x times x. The square root of 1 is 1. And to multiply to get a minus, it's a plus and a minus, correct? So that factors into x plus 1 over x minus 1. That first one is over x minus 1. I've rewritten the first fraction. Minus. Rewrite the second fraction. X squared minus 1, again, will factor into x plus 1, x minus 1. This time the denominator is x plus 1. What is so nice about the way that worked out? Things cancel. If you look at the first fraction, there is a factor of x minus 1 in the numerator and denominator, so x minus 1 can cancel, leaving us with x plus 1. In the second fraction, what happens? A factor of x plus 1 cancels, correct? Leaving us with X minus 1. What are we doing with that X minus 1 though? We are subtracting it. So I'm going to say minus the quantity X minus 1. So what's this read if we distribute that subtraction sign? It's X plus 1 and then what? Minus X, and then minus negative 1 is plus 1. X minus X vanishes. And then we end up with 1 plus 1, which is 2. What was our goal? To prove that it equals 2. Did we do logical steps that brought us to an answer of 2? And that's the idea, is that we're using logical steps. When it comes to trig, we'll use identities and other various things to get us to that point. But our point here was we got to the equal 2. So, I mean, I guess if you're looking to box an answer, that's what you're boxing. But you can even just put a check. Or honestly, you don't even have to put anything. Okay? Because here's what it comes down to. When I grade these, and notice I said when I grade these, because the only way you can really know if you're doing them right, well, 1, you're getting the left and the right to equal each other. But 2, I'm going to be grading these. Because when it comes test time, I want you guys to know if you've been doing them right or not. So this is one of those homeworks I'm going to grade, and I'm not grading the answer. Because does it make sense if I say the answer is provided?
Yeah.
Here's the starting problem. Here's the answer. We were already provided that, right? What I'm grading is the middle stuff. So your steps have to be logical. They have to make sense. They have to flow. You throw in a bunch of gibberish that doesn't make sense, I can't give you the points. Am I making sense with what I'm saying there? Okay, so it's the middles that matter. So often, if I'm in a quick grade mode, I'm just checking the final answers. I'm not necessarily checking the middle. On tests, it's hit and miss. Sometimes I check the middle of the problem, sometimes I don't. Here, that's the whole point of it. That is what I'm checking, is the middle of the problem. Okay? So notice, a couple of things to point out real quick before we move on. I'm going to start with the left usually. Okay, so I started with the left. I didn't touch the right. I just manipulate everything till I got to the right. And that's what I'm going to encourage you guys to do. Okay? That's using your algebra skills. We're ready to use some trig skills now. Not that you have a choice in the matter, right? So let's look at example 2. So on the left, we're going to start with tangent x plus cotangent x. And that's what we're going to finagle. Okay? There's probably a better mathematical word than finagle, but it's what we're doing, right? And what is our goal in the end? Our goal in the end, and sometimes it helps to see what the goal in the end is. I really do believe that, okay? I mean, at the beginning, it's hard to tell, okay, I don't know how we're going to get there, but once you start seeing some things, it's good to see, so this is what we're going to work with. This is our goal in the end. I'm not doing anything with this secant, cosecant, I'm just trying to get there. So thoughts on what I can do with tangent x plus cotangent x?
Or you can use the Pythagorean identities to do it. Secant squared minus 1 cosecant squared minus 1.
Cannot use Pythagorean identities yet.
I would use the quotient identity.
Okay. I like the idea of quotient identities. Why can I not use Pythagorean identities yet? Why do I have to veto Jace at this point? They're not what? They're not squared, yes? It's that so easy mistake that we all make. To use the Pythagorean identities, they have to be squareds. These are just a regular tangent, cotangent. Okay? So, Hansa mentioned quotient identity. Basically, that means changing everything to sine and cosine. Was that one of our 5 suggestions? Change everything to sine and cosine. So, tangent can be rewritten as sine x over cosine x, plus cotangent x can be rewritten as cosine x over sine x. That sounds familiar, right? Okay. Need another plan now, another step. I'm not sure what you mean.
Like the sine x is 1 over cosine.
Okay, so I'm at a spot where I see two different directions we can go, because that's not the direction I went, but I can see going that direction. Okay, so the suggestion was that basically we take our sines and cosines and change them to secants and cosecants, is the suggestion I'm being given. And that is doable. Yes, it looks like fractions within fractions, but they can be flipped so that they're not fractions within fractions. And then it comes down to that you're working with secants and cosecants. So that is one option. And it just basically flips the steps I'm going to do here. Any thoughts on another option? I'm just kind of debating which way I want to go. Which way I want to lead you guys, I guess. I didn't encourage it up above, but I would support it here. Two fractions being added, get a common denominator and put them as one fraction. And here's what I'm going to say. If we put them together right now as one fraction in terms of sines and cosines, right, we will eventually flip to secants and cosecants, obviously, because that's where our answer is. If you go ahead and flip to secants and cosecants now, it just means that you'll get a common denominator in terms of secants and cosecants, and you'll already be in the right piece there. Now, here's my thought. What are you guys more comfortable working with? Sines and cosines or secants and cosecants?
Sines and cosines.
See, that's my gut, is that you guys are going to be more comfortable working with sines and cosines, but I get why you're suggesting secants and cosecants. So this is one of those, when I grade your stuff, it just has to flow. It has to make sense, right? Is everyone going to take the exact same steps to get to the final answer? No. I have problems on my answer key where I have 3 or 4 different ways worked out, just depending on what steps people take. Okay? I'm going to go the sine cosine direction, but that's not to say that you couldn't do an equivalent thing in secant and cosecant. Okay? If I'm getting a common denominator right now, what is my common denominator? Cosine x sine x, right? The two together. So, cosine x, sine x. Remember how I do this? What is my first denominator of cosine x missing? Sine x. So what am I multiplying this first fraction by? Sine x. What you do to the denominator, you do to the numerator, yes? So in my numerator, what is sine x times sine x? Sine squared x. Plus, because we're adding these two fractions, what is my second denominator missing? It currently has sine, so it is missing a cosine x. If I multiply that denominator by cosine x, you're multiplying that numerator by cosine x. What's cosine x times cosine x? Cosine squared x. What do you know? What equals 1? Sine squared x plus cosine squared x is a Pythagorean identity. Remember when I write PI that you can't see, that stands for Pythagorean identity. So we can take that numerator of sine squared x plus cosine squared x and replace it with 1 over cosine x sine x. Should reverse that arrow on top, but. And this is where it helps to know where are we going, right? What do you notice here?
That 1 over cosine x sine x is equal to secant x.
Yeah. The reciprocal of cosine x is secant x. The reciprocal of sine x is cosecant x, yes? I mean, if you want a better visual, I guess, you could break this into 1 over cosine x times 1 over sine x. But the idea is when you take cosine x out of the denominator, it becomes secant x. When you take sine x out of the denominator, it becomes cosecant x. And where was I supposed to end up? Right there, secant x, cosecant x. If you had changed up here to secants and cosecants, you would have had what? Secant x over cosecant x plus cosecant x over secant x, I think. And you could have done the same type common denominator thing. The Pythagorean identity would not have been as easy, though. That's the one place I see a difference. So, okay, questions. It's going to be the same thing we had in last lesson. You can follow my steps, right? The challenge is going to be creating the steps on your own. Okay? Now, the good news is you've been through lesson 5.1, even if it was a week and a half ago before spring break and all of that. You've been through it. You just have to dig it out of the backs of your brains a little bit. So, it's there. You're familiar with these steps. It's just a matter of making it happen. Okay? You got the idea of how to begin this? We're going to start with the what? So I'm going to start with 1 over secant x minus 1 plus 1 over secant x plus 1. That's what we're trying to work with. What's our goal when we get down to the end? Two cotangent x cosecant x. That's my goal. And it's not that you have to write it down there ahead of time, but that's my visual for you. Of, okay, this is what you need to keep in mind. This is where we're headed. I would go for reciprocal identity if I didn't have the minus 1 and plus 1 here. I can't use the reciprocal identity with that minus 1 plus 1 there. Okay, if it was just 1 over secant x, in a heartbeat, I'd be going for our reciprocal identities to get these out of fraction form. But because of that minus 1 and plus 1, I'm going to have to take a different direction. And we got another suggestion. Okay, and I would support common denominator here. I think some of you guys are gun shy because I had to shoot it down earlier. And here's the thing. If I think common denominator, what's my common denominator going to be between these? Okay, he says secant squared x minus 1, but where does that come from? That comes from secant x minus 1 times secant x plus 1. So yes, we're going to have to take these two factors and make them our common denominator. And for the first step, I'm just going to write it out as secant x minus 1 times secant x plus 1. If you want to go ahead and FOIL that together, you can. I will in my next step. So, if this is my first fraction of secant x minus 1 is my denominator, what am I missing in the denominator? I'm missing a secant x plus 1, correct? So if I multiply this denominator by secant x plus 1, what do I have to do up here? I'm multiplying my numerator by secant x plus 1. Kind of a silly question, but I'm going to ask, what is 1 times secant x plus 1? Secant x plus 1. Then we're going to be adding. Okay, second fraction. Denominator currently is secant x plus 1. What am I missing in this denominator? Secant x minus 1. If I multiply the denominator by secant x minus 1, you got to multiply the numerator by secant x minus 1. What is 1 times secant x minus 1? Secant x minus 1. Are we okay there? Okay. Numerator. What do you notice about the numerator? What cancels? The ones cancel. What's secant x plus secant x? 2 secant x. So my numerator goes to just being 2 secant x. It's kind of like me saying, what's x plus x? And you're supposed to say 2x, right? So what's secant x plus secant x? 2 secant x. Now, these denominators, I say you just kind of, sometimes you want to FOIL, sometimes you don't. It just depends on the situation. And on this one, I see what happens when we FOIL here. And so you're going to want to FOIL. Especially since these are conjugates. Remember what happens when we multiply conjugates? Yeah, because these are the same things, just different middle signs, the middle terms will cancel, right? So if we FOIL, secant x times secant x is secant squared x. My outside would be a plus secant x. My inside would be a minus secant x, so those cancel. Minus 1 times plus 1, minus 1. And that what? So if you need a note to yourself, what we did right there, we did FOIL. In the denominator, if you remember from before break, I would always kind of try and say, if you see any combination of squareds and ones being added and subtracted, right? Squareds and ones being added and subtracted. You want to think, is this a Pythagorean identity? What is the Pythagorean identity that relates to secant squared and 1? Yeah, side note over here. 1 plus tangent squared x equals secant squared x, right? This is kind of my side note area. Okay, so if 1 plus tangent squared equals secant squared x, then what do we know about secant squared x minus 1? Subtract the 1 over, and we have that tangent squared x is equal to secant squared x minus 1, right? So if you see a secant squared x minus 1, it can be replaced with tangent squared x. So let's do this. I still have 2 secant x on top. And now I have tangent squared x on bottom. Okay. I'll be honest, this is where I always have to kind of pause and, okay, I've done all this work. Where am I going? Right? What was my goal again? 2 cotangent cosecant. Well, good news is I see the 2, right? So it just comes down to manipulating these guys. And I don't know, there's a couple different ways we could do this, so. Have you guys tried anything? You could go to sine and cosines. Yes, that would work. If we go to sine and cosines, okay, if we go to sines and cosines, we're going to have fractions within fractions, aren't we? Which is doable because you just divide them and make them not fractions within fractions. If we want, okay, so side note before we, how can we get tangent squared out of the denominator? Well, but we can't multiply by tangent squared because this isn't an equation. We don't have both sides we can multiply by. But okay, and maybe I should just go that way. Maybe I'll just go the ugly fraction way because my other thought was tangent squared. What's tangent the reciprocal of? Tangent is the reciprocal of cotangent. And so tangent in the denominator is equal to a cotangent not in the denominator. So like as I look at my notes, my next step I wrote out is 2 secant x, and then to take the tangent out of the denominator, I wrote it as cotangent. And then I changed everything to sine and cosine. Now, if you would rather write it as sines and cosines and then go out of fraction form, we can do that too. It's the same number of steps. So you guys want me to go sine and cosine right now then? Is that what you see? Okay, and again, the only advantage here is I'm staying away from fractions. So a tangent squared, if I keep this as 2 secant x, reciprocal of tangent is cotangent squared. So that is an equivalent statement. And I can use the reciprocal identity because there's no like plus 1, minus 1. It's just that one function. And now I am definitely good with the idea of, okay, let's think in terms of sines and cosines. The whole number 2 is a whole number 2. What is secant? The reciprocal of cosine. So 1 over cosine x. What is cotangent squared x? Cosine squared x over sine squared x. What's one thing you see that can happen? 1 cosine on bottom cancels with 1 cosine on top. So cosine x cancels with 1 of the cosine x's on top. You see the 2 out front. And then on top, we still have a cosine. On bottom, we have sine squared. Think ahead to your answer. What do you know about cotangent? Cotangent is cosine over sine, correct? What is cosecant? The reciprocal of sine, so 1 over sine. Do I have those pieces? And that's, you just kind of have to show that you have those pieces. And so the idea here, I have a cosine on top. I have 2 sines on bottom. So you can break this up into a cosine over sine times a 1 over sine if you want. Or you could just write it as cosine x over sine times sine. You know, it's all there. Notice I had a cosine on top. I still have a cosine on top. I had sine squared on bottom. Do I still have sine squared on bottom? I do. Because sine times sine is sine squared. Do all my pieces match now? 2 cosine over sine is cotangent x. 1 over sine is cosecant x. We got there. Obviously, you saw some different directions you could go along the way. All your middle steps don't have to match mine. They just have to flow. They just have to make sense. You get there a different way, I will follow the best I can. And usually by the time I get done grading homework, I kind of know the different directions people have gone. Okay? Okay. What is the first one on back? Okay, let's go ahead. May or may not get through. As I said, in my notes, all I had done last year, or no, 2 years ago, was just example 4. I did not do example 5. Okay. My job, I am starting with cosine t over 1 minus sine t. My goal in the end, one plus sine t over cosine t. And this is where I'm going to have to probably give you a suggestion of a direction to go here. I mean, it's already in terms of cosine sines. I don't know. I'm trying to think if there'd be a way. No, there wouldn't really be a way to split it. So 1 minus sine t. What is the conjugate of 1 minus sine t? 1 plus sine t, right? Remember conjugate? Same pieces, just change the sign in the middle. If we multiply this denominator by 1 plus sine t, we're going to head a direction towards a Pythagorean identity. Now, we can't just multiply the denominator by something. However, what you do to the denominator, you can do to a numerator. And so the suggestion I'm going to have is that we're going to multiply numerator and denominator by 1 plus sine t. We're picking 1 plus sine t because it is the conjugate of the denominator. And this is kind of a technique like you remember when we're trying to when we're trying to rationalize and get rid of radicals. It's the same technique. Okay, on top, I'm not going to multiply, I'm just going to leave it. So on top, I'm going to write this as cosine t times 1 plus sine t. And again, I guess I should have talked about why I did that. I'm trying to watch time though too. Do you see why I didn't multiply it? What am I trying to get my numerator to be? 1 plus sine t. Do I have a factor of 1 plus sine t here? I do. Okay, we need the cosine to cancel. We're headed there. Or we need a cosine to cancel. What happens when we FOIL these? One times 1 is 1. Outsides and insides will cancel. And then I have minus sine squared t. What is that looking somewhat like? A Pythagorean identity. The Pythagorean identity we know is sine squared t plus cosine squared t equals 1. So again, this is my side notes box, right? If you don't need this, don't do it. So if what do I need to do? Subtract the sine squared over. So then I'm going to have cosine squared t is equal to 1 minus sine squared t. Is there a reason I did that? Yeah. If cosine squared is equal to 1 minus sine squared, I can replace it. So I still have cosine t times 1 plus sine t on top. In the denominator, 1 minus sine squared is going to be replaced with cosine squared. And
Get rid of one of the square, or the cosine.
a single cosine on top can cancel with a single cosine on bottom. If I do that, I now have 1 plus sine t on top over cosine t in the denominator. Okay? So that was a technique I wanted to show you there. Okay, here's what I'm going to say. I don't know they'll necessarily do example 5 tomorrow, unless you guys find a reason you need me to. I'm probably going to focus more on your questions tomorrow. So what I want you to do today is go through the homework. Are you going to magically do every single problem? Probably not. It's going to be one of those where, this is my plan tomorrow is to talk about some of these. Now, okay guys, do you understand what I mean when I put this homework up here? Use your big math brains here. Page 418, 12 through 39, multiples of 3. 12, 15, 18, 21, 24, 27, 30, 33, 36, 39. I think there's 10 problems if I just counted right. So, I will write them here in case you need them. One, two, 3, 4, 5, 6, 7, 8, 9, 10. It is 10 problems. Sounds like a lot, but it's not.
So are we going to be turning it in the class tomorrow? So we want to have a general idea of everything done.
That will be my general intention. I didn't get that said, so I might cut slack and, accept at the beginning of the next day, but not really offer help at the beginning of the next day.